Hi, everyone, and welcome to today's Tech Talk on Amazon QLDB. My name is Chirag Dole. I'm a senior PMM for Amazon QLDB. And with me today is Sid Sanyal, principal TPM from our team. We have a packed agenda today. We will cover the AWS's approach to purpose-built database. Then we will dive deep into why we chose to build the Ledger database. How does Amazon QLDB work? And then the building blocks on building your first Amazon QLDB application. We are hoping to leave around 8 to 10 minutes for Q&A. So let's jump right in. At AWS, we believe that seldom can one database fit the needs of multiple distinct use cases. In the past, web applications were constructed by using the LAMP stack, where a single database was used for many different experiences. In contrast, today's web applications from customers such as Expedia, Airbnb, or Capital One do not use single database. They use several different types of databases. A one-size-fits-all relational database as the only store for your application no longer works. So developers are doing what they do best, breaking complex applications into smaller pieces and picking the best tool to solve each problem. This ensures that the applications are well architected and can scale effectively as the application demand grows. The best tool for a job usually differs by use case. So developers are now building highly distributed applications using a multitude of purpose-built databases. For each of these data categories, AWS provides various purpose-built databases. The topic at hand today, though, is a ledger database. And you may ask why we chose to build a ledger database. As you may know, ledgers are not a new concept, and they have existed for thousands of years. Record keeping has been a central theme to civilizations around the world, and they have had to deal with the same kinds of problems that we deal with today. Traditionally, ledgers have been a book or a collection of financial accounts of a particular type. And today, we use things like an audit table or an audit log in a relational database to solve the same problem. Ledger applications are used in banking, in manufacturing, as well as for maintaining any type of asset ownership or for asset provenance. So they have a wide and broad use. Now you may ask, what is the problem with the current model of building ledger applications? Well, today, typically customers are doing this with a relational database and using some sort of an audit trail or an audit log. However, this type of implementation, it's hard, it's complicated, and it's expensive. You have to use concepts like stored procedures and triggers. And when the database application needs to scale, the audit functionality can slow things down. Also, another really important point is that a relational database is not inherently immutable, which means that a record can be updated or overwritten. So there is no way to verify that someone who has full access to the system has not accidentally altered the data. Additionally, some customers are trying to use blockchain frameworks, which consist of decentralized ledgers. However, blockchain networks are meant for different purpose, specifically for decentralized use cases where there are at least two or more parties or peers who are working together. So this setup can cause unnecessary complexity for customers who just need a centralized application with some sort of a ledger. Now, to address these needs of our customers, in September this year, we announced the general availability of Amazon QLDB, which is a purpose-built ledger database, and that provides a transparent, immutable, and cryptographically verifiable transaction log. QLDB is immutable. Thanks to its journal, the records in QLDB cannot be altered. Now, a great analogy to think of what a journal looks like is a string of pearls. The journal is append only and sequenced. All operations for a journal, including updates, deletes, everything is written to the journal. There are no APIs or other methods to alter a data that's once been committed to the journal. So this capability allows QLDB and the applications built on top to be immutable. QLDB is also cryptographically verifiable. It uses cryptography to create a concise summary of the whole change history. This summary, which we call as a digest, is generated using a cryptographic hash function called as SHA-256. The digest acts as a proof of your data's change history, allowing you to look back and verify the integrity of your data. You can use the digest easily with QLDB's API to prove the integrity of any transaction. For example, whether a transaction really occurred or not. While QLDB also allows you to query and access your data's history, verifiability is useful for business scenarios where you need a proof related to a specific transaction. For example, an e-commerce business may need to show proof of a winning bid. Now you may ask, at a broad level, why does immutability and verifiability matter to a business? Well, first, it allows you to reduce risk. It ensures the safeguarding of critical system of record applications where data loss could be really expensive. It allows you to improve data tracking. It helps you or any parties that you're working with who want to have access to the system to quickly and accurately track data's entire lineage, improving efficiency in the tracking of the source of such issues. For example, tracking a manufacturing defect or maintaining supply network data hygiene. It allows you to do auditing easily. It helps reduce downtime caused due to audit and compliance issues, saving hundreds of productivity hours for your team. And finally, it reduces implementation effort. Building immutability and verifiability in a traditional database application is very time consuming, complex, and expensive. And leveraging a purpose built tool like QLDB, you can achieve that easily. When performing a database operation, Amazon QLDB provides ACID properties, making it easy to write correct applications. Also, QLDB transactions have full serializability, which is the highest level of isolation. There is absolutely no risk that you'll see phantom reads, write skew, dirty reads, or any other issues. Additionally, QLDB delivers seamless automatic scaling to meet the demands of your application without any need to provision capacity or configure read and write limits. Amazon QLDB is also highly available because your data is replicated across 3 AZs in an AWS region without any additional cost or setup. QLDB continuously backs up your data while maintaining consistent performance, allowing you to transparently recover from any instance or physical storage failures. Now let's take a deeper look at how QLDB actually works. In this image, we are showing you an example on how QLDB works. Like any database application, you will write data into QLDB. When data is written to your QLDB ledger, it is first committed to the journal. The journal provides immutability and verifiability by storing a log of each transaction in a sequenced way and by using cryptographic techniques. The data is then written to the current state and index tables, which, as the name suggests, stores the current and historical values of your data. Now you may ask, how does an update work? Well, when an application needs to modify data in a document, it does so in a database transaction. Within a transaction, data is read from QLDB, updated, and committed to the journal. QLDB writes one or more chain blocks to the journal in a transaction. Each block contains entry objects that represent the document revisions that you insert, update, and delete. This image shows that a block is committed to the journal during a transaction and results in document revision entries within that block. It also shows that each block is hashed for verification and has a sequence number to specify its address. Now, we'd like to quickly touch upon some basics around cryptographic hashing because these are important concepts on how QLDB works. QLDB uses SHA-256 as its cryptographic hash function. So each hash is a 256-bit value. And as you may know, hash functions provide encryption using an algorithm and no key. They are called one-way hash functions because there is no way to reverse the encryption. A variable length plain text is hashed into a fixed length hash value, which is often called a message digest or simply a hash. Also, as you can see at the bottom of the image, with hash chaining, you can concatenate multiple hash values into a new 256-bit value. Another important concept in QLDB is Merkle trees. Now, as you may already know, a Merkle tree is a tree data structure in which each leaf node represents a hash of a data block. Each non-leaf node is a hash of its child nodes. This concept is commonly used in blockchains. A Merkle tree enables efficient verification of large data sets with an audit-proof mechanism. And at the top of this image, you can see a Merkle root or a QLDB digest, which is the hash of all the hashes of all the transactions that are part of a block in a blockchain. Now, we have used a similar concept in QLDB. The diagram in front of you illustrates the Amazon QLDB Merkle tree implementation. And via this, we will talk about how you can verify a document in QLDB. This diagram shows a set of block hashes that roll up to the top root node, which represents the digest, or as we previously learned, a Merkle root. Now let's assume node A is the block which contains a document whose integrity you want to verify. You will follow 4 simple steps. First, you will request the digest from QLDB. Second, you will request the proof, which consists of B, E, and G as the nodes which represent the ordered list of hashes that QLDB will provide for your proof. Now, if you carefully look at this diagram, the B, E, and G hashes are required to help you recalculate the digest from hash of node A. Using the client-side API, we can recalculate the digest using the proof. To do this, start with hash A and concatenate it with hash B. Then hash the result to compute D. Next, use D and E to compute F. And finally, use F and G to compute the digest. This verification is successful if your recalculated digest matches the expected value. Now remember that if it's a match, it's not mathematically feasible to reverse engineer the hashes in a proof. Therefore, this exercise proves that the contents of your document were indeed written in this journal location relative to the digest. And now I will hand it over to Sid Sanyal, who will introduce the concepts for building an application on QLDB.
Thanks, Chirag. Let us now look into the basic concepts that would enable you to build applications that access data in QLDB. In order to make development easy, we adopted the philosophy of open sourcing our clients, frameworks, and utilities that you can use to build applications on QLDB. Now, let us look into the key aspects of QLDB that enable ease of development. QLDB supports the particle query language, wherein particle provides SQL compatible query access across multiple data stores containing structured data, semi structured data, and nested data. Particle is used widely within Amazon and is now available as part of many AWS services, including QLDB. QLDB supports a flexible and schema-less approach to storing data. Data in QLDB is stored in the form of ION documents. The ION document format is an open source specification that was built within Amazon and is being adopted across many internal Amazon teams. Amazon ION was built for scale and for ease of use, and we are happy to be supporting ION as a primary data format. QLDB also supports traditional database features such as asset transaction, serializable isolation, which enable developers to apply traditional concepts, programming concepts with QLDB. We have also provided a number of purpose-built drivers, which are client SDKs in the popular languages such as Java, Python, Node.js, which have been open sourced as well. For each of the drivers that we have open sourced, we have also contributed a getting started tutorial in the corresponding language, which you can use to get acquainted with the programming primitives that you need to use to build an application with QLDB drivers. Now, before we go any further, let's understand and map the constructs between a relational database system, a traditional relational database system, and QLDB. So, in a traditional database, such as Postgres, is referred to as a ledger in QLDB. A table and an index in a relational database would map to a similar concept in QLDB as well. However, a table row or a tuple in a relational database would correspond to an Amazon ION document that is stored within QLDB. And a column in a traditional database or a relational database would now map to an attribute that is contained within an ION document in QLDB. Like I touched upon earlier, the traditional SQL syntax that you use for querying data in a database is you can now use the particle query language, which is essentially based on the SQL query language to access data in QLDB. The concept of an audit log in a relational database corresponds to what we call the journal in QLDB. Now, as we touched upon earlier, let's look into Particle or some of the fundamental design tenets of Particle that will enable you to understand how to write queries. Particle's extensions to SQL are easy to understand, treat nested data as first class citizens, and compose seamlessly with each other and with SQL. So, this enables intuitive filtering, joining, and aggregation on the combination of structured, semi structured, and nested data sets. Particle also enables a unified query access across multiple data stores and data formats by separating the syntax and the semantics of a query from the underlying format of the data, or perhaps the data store that is being accessed. It enables users to interact with data that may or may not have a regular schema. So there are definitely a lot of advantages of using Particle for operating on a document-based database. Now let's look at a basic Particle query. If you look at the left-hand side, wherein we actually have a document, which is essentially a record of indicate for a vehicle registration data, you can see that the query on the right-hand side appears very similar to a traditional SQL query, where we have the select statement, which has the select from where structure. In this case, in this particular query, we are selecting the VIN, the property VIN, from the vehicle registration table, which is referred to as an alias using the as clause. And we have specified a predicate where the city has a conditional, equal conditional operator, where the city is Seattle. And Seattle in single quotes is a string literal. So this query is essentially retrieving the VIN numbers, the VINs of all the vehicles that are registered in the city of Seattle. So select s.vin as VIN. So we can support an alias from the table vehicle registration, aliased as s, and that alias s is used in the predicate, where we use the attribute city. If you can see on the left hand side of the structure, the attribute city is a top level attribute and can simply be referred to as table dot attribute name. So where s being the table vehicle registration, where s dot city is equal to Seattle. So this provides for a very simplistic and traditional use of the particle syntax. Now let's look at a slightly more advanced case where we have a nested collection. In this case, you can see from on the left hand side that the owner's attribute is essentially a nested structure which contains two attributes, primary owner and secondary owners. Again, primary owner and secondary owners, both of these attributes are essentially structs. They themselves are structures which have an ion representation, ion document representation themselves. Now, on the right hand side, the query is about finding out the VINs and the secondary owners of vehicles where the secondary owner of a particular vehicle has a particular value. In this case, we start with the vehicle registration table referred in the from clause from vehicle registration aliased as s. The alias of s is then used to navigate to the owner's attribute, which is again a struct. So s dot owners is referred to as o, aliased as o, and we use this alias, the struct, the owner struct itself, to traverse further below into the secondary owner's attribute. So we are going from the top level of the document right to the bottom of the document to reach the person ID. So dot s dot owners gives us the owner's structure. We can use the owner structure to go to the secondary owners. So o dot secondary owners gives us the secondary owner structure, which is now referred to as P, aliased as P. And we can now specify the attribute of person ID that is contained within secondary owners and apply an equal condition operator for the value that is given in the string literal as 5u, fgdl, and so on. So this actually allows us to construct a query where the predicate is one of the deep nested attributes inside a nested structure, and still be able to construct a simple select from where statement for this particular query. And in the output, as you can see, because in the select statement we had used we have specified VIN as an alias of VIN, and the person ID as an alias of person ID, you can see that the output contains only two attributes, VIN and the person ID. Where in this case, the person ID is that of is one of the secondary owners of the vehicle. Essentially, this shows you how to navigate and construct a query for a nested document. Now, some of the supported particle statements in QLDB may appear very familiar because they have a SQL-like syntax. We can cover them further in this presentation. We also support a number of particle functions and operations in QLDB. You can actually use them for some more advanced use cases, but there's a rich set of these functions and operations available for you to use. Particle in Amazon QLDB essentially works on both standard aggregate functions as well as scalar functions. Now let's quickly touch upon Ion. So in Ion, Amazon Ion is a richly typed, self-describing hierarchical data serialization format offering interchangeable binary as well as text representations. The text format, which is essentially a superset of JSON, is easy to read and author. It supports rapid prototyping as well. The binary representation is efficient to store, transmit, and perform skip scan parsing operations. The rich type system provides unambiguous semantics for long term preservation of data, which can survive multiple generations of software evolution. ION was built to address rapid development, decoupling, and efficiency challenges faced every day while engineering large scale architectures. ION, like we saw earlier, ION supports both the primitive types as well as collection types. The SQL scalar types that you find commonly are covered by their ION scalar counterparts. The scalar counterparts being string, int, float, decimal, timestamp, so on and so forth. Ion actually adds support for specific number types, in which you can now be more specific about the type of the number that you're trying to store, which could be an int, it could be a float, it could be a decimal. Ion also introduces an explicit data type called timestamp, in which you can actually manipulate timestamps as you would expect in native languages. Now let's take a quick glance at how an Amazon Ion document looks like alongside a traditional JSON document. From the outset, you can see that they appear very identical to each other. There are some minor differences, but here I would like to highlight that if you look at the comments on the right hand side in the Amazon Ion document, the attribute ENG size is a decimal and it is distinct from the attribute curve weight, which is specified as an int. And that is where Amazon Ion can be used as a richly typed system to enable you to reduce the amount of errors you can actually traditionally encounter while dealing with a generic number type in JSON. So similar to JSON, you compose Amazon Ion documents with a set of primitive data types and a set of recursively defined container types. Fundamentally, QLDB stores data into tables of documents. More precisely, tables are collections of document revisions. And a document revision represents a single iteration of the document's full dataset. Because QLDB stores the complete change history of your data, a table contains not only the latest revision of its documents, but also all its prior iterations. QLDB provides queryable views of your data based on the transaction information that is committed to the journal. Similar to views in relational databases, a view in QLDB is a projection of the data in a table. Views are maintained in real time so that they are always available for applications to query. So you can query the following views. You can query either the user view, which is the current view, or you can query the committed view of the data. The committed view is the latest non-deleted revision of both your data and the system generated metadata. This is the full system defined table that corresponds directly to your user table. We'll touch upon more, we'll use this committed view in our examples further. However, let's take an example of what happens when a document is inserted into QLDB. We commit this transaction into the journal. The data is committed to the journal in an append only manner. And from this journal, we then generate the current view and the historical view of data in an indexed manner. So we are maintaining two structures here. We are maintaining the current view and the historical view. Again, reiterating, in QLDB, a document revision is a structure that represents a single iteration of a document's full data set, which includes both your business data as well as the system generated metadata. Each revision of a document is uniquely identified by a combination of the document ID and a version number. So as you can see from this example, when this record was actually inserted, two things happened. We picked up the latest commit of this data from the journal and applied it to the current view of the cars table, denoted by C, and the historical view of this data, which is H. Once the data is committed to the journal, we apply this data from the append only journal into two views, into the cars, current view of cars, and into the history view of cars. The current view of cars can be thought of as a traditional database table that is available for querying by your applications. The history view is essentially a function that we have built within QLDB that provides you with both the document's data as well as the revision metadata, which includes the document ID, the transaction time, etc. Now let's see what happens when we modify an attribute in the previous record that was inserted. In this case, we update the cars document wherein we change the owner to a new value to Ronnie Hash for a particular car with the VIN 12345, as you can see on the query over there. In this case, the transaction is committed to the journal, essentially appended to the end of the journal, and from the latest append that we have applied to the journal, we apply the changes to both the current view of the data and the historical view of the data. The current view of the data is essentially one record which contains the latest values that are contained in the document, and the historical view, we actually add a record which is essentially a document revision that we have added with the latest data that was applied. And this document revision contains both the entire data set, which is all the attributes of the cars record, as well as the metadata. The metadata, as you can see, includes the document ID and the version number. And in this case, when Ronnie Hash was made as the new owner, we added a new entry in the historical view in which the version number has been appended by 1. So it has increased from 0 to 1. We have noted down the transaction time, and we have also appended the version number. So this way, QLDB maintains an immutable history of all the changes that have occurred to the cars record or the cars document in the journal, and we have applied the latest view of that data in the cars table and all the document revisions that have occurred thus far in the history view. QLDB stores data records as documents, like we mentioned earlier, and these documents are essentially just ion struct objects that are inserted into a table. For the vehicle registration example, let's assume there are 4 tables: the person, who could be an owner of the car, a driver's license, the vehicle, and the vehicle registration. Now, on this, using this simple example, let's look into how would we construct these tables. Like we mentioned earlier, QLDB is based on a schema-less approach, in which we do not need you to specify a schema upfront. I can create the person table, driver's license tables, and the remaining 2 tables simply by executing one particle statement: create table person, or create table driver's license, and so on and so forth. You do not need to know the schema upfront, because the schema is going to be determined or inferred essentially based on the ion documents that you insert in each of these tables. Moving further, let's look at the vehicle registration application example and look at what are the logical entities and relationships involved here. As you can see, we have vehicle, person, driver's license, and vehicle registration entities. And how we can model them is the concept of owners can be modeled within the vehicle registration entity itself. Now, to give it a physical representation, the vehicle registration entity can be a document, which is essentially a struct and contains top level attributes such as VIN, license number, state, city, etc. And it also contains a nested structure such as owners, as depicted by owners, which contains again 2 attributes within itself: the primary owner and secondary owners. As you can see, the primary owner itself is again a struct in which there is only one attribute known as the person ID. Now, what is important to note here is that you can identify certain fields as indexes based on their selectivity. So if you can create an index that has high selectivity, which means a query using that particular index gives you only one particular record or as few records as possible, then that's going to be a good candidate to be an index field. So in the case of the vehicle entity, we have used the VIN number as the primary key. In the person table, however, you have 2 choices. One is to have an index on the gov ID, the government ID, which could be a social security number or the driver's license number or the passport number, and so on and so forth. Or you could also use the implicit document ID, which is essentially a part of the document's metadata and uniquely identifies that particular document in the table. In this case, because of the sensitive nature of the gov ID, we are going to be using the document ID, which is part of the metadata of the person table, as a foreign key for use in the vehicle registration table and in the driver's license table. This way, you do not need to propagate the gov ID from the person table across all your other documents. So in this case, the person ID in the driver's license table is essentially the document ID of that particular person document in the person table. Similarly, the owner in the owner's attribute of the vehicle registration table, you can see that the primary owner is essentially the person ID or the document ID of the person that is the primary owner. And in the secondary owners, we have applied a similar concept in which it's again a person, and we use that person records document ID. Armed with these concepts, let's move on to the next step of actually defining the indexes. And creating an index is as simple as executing a query statement, a particle query of create index on the table, and in brackets you specify the attribute name. And this attribute name is based on the attribute names you specify in documents that you insert into that particular table. Now moving on, the question is, how do we model this data? How do I visualize this data in QLDB? So as you can see, I'm using a flexible document schema that leverages Amazon Ion. I don't really have to know upfront what particular table schema to use. So in this case, I insert a document into the person table with certain attributes such as the first name, the last name, the date of birth, gov ID, etc. And I also insert a record into the driver's license table, wherein I have the usual attributes like license number, license type, etc. However, what is to be noted here is that the person ID attribute in the driver's license table has the value of the document ID that corresponds to the person to whom this driver's license belongs to. So we have taken the document ID of the license holder from the person document or the person record for Raul Lewis, and we have applied that document ID in this particular driver's license table. So even though we have used the license number as an index for the driver's license table, theoretically you could use the person ID as an index field for queries as well. So using the document ID, which is part of the metadata of a particular document, as a foreign key is essentially usually a good idea. Moving on, let's look at the nested structure. Here we have purposely decided to create an owner's struct object. If you can see that we need both the primary owner and the secondary owners. We could have had a separate table called owners and then done another relationship with that table. But in QLDB, it's actually very efficient to store the data in the same document, so to speak. So there's a lot of choice available to the application developer to decide, do I want to have what sort of relationships do I want to create between my documents? And it's absolutely fine to add structured or nested structures in one document. Let's look at the scenario. In this particular scenario, we are going to be showing how to use certain particle queries to achieve certain outcomes. So in this case, the outcome that we are trying to seek is to transfer the primary ownership of the vehicle to another person. And as we noted from the vehicle registration table, the document contained two attributes. In the owner's attribute, there were two distinct attributes, the primary owner and the secondary owners. So in this case, we are going to be modifying the value of the primary owner to be that of a different person. So in step one, we get the document ID for the new owner, which is Brent Logan, from the committed view of the person table. And this is what I had mentioned earlier, that we can access this metadata by querying the committed view. So if you want the document ID for a particular document, you can query the committed view. This view returns documents from the system defined table that directly corresponds to your user table. It includes the latest committed, non-deleted revisions of both your data and the QLDB generated metadata. So in order to query this view, you will actually have to add the prefix of underscore QL underscore committed to the table name in your query. The prefix underscore QL underscore is reserved in QLDB for system objects. So in this case, we will select the from the metadata portion of this particular committed view. We are going to select metadata.id from the committed view of the person table, and we give it an alias of p, where p.data, again p.data is referring to a particular struct in the committed view of this table. P.data is a struct which contains an attribute called first name, and we have applied an equality condition where it's the value is a string literal of Brent, and similarly the last name is checked against Logan. So the equality operators are operating on the first name and the last name of the data portion of the committed view. So in this case, the query returns, say it returns a particular document ID. We can now use this document ID in step 2 to update the primary owner in the vehicle registration table. So the query would be very similar to how you would create a traditional SQL query, in which you update the vehicle registration table, refer to it as R as an alias, and in R, for a document in R, you set the value of the struct of the attribute person ID that exists inside a structure called primary owner, which itself exists inside a structure called owners, for the condition where the VIN number is a particular value. So in this case, you can navigate from the top of the document structure right down to a particular nested attribute in a particular collection by specifying the path to that particular attribute, where owners is the top level struct attribute, primary owner is a nested struct attribute, and the person ID is a scalar. So you can set r.owners.primary owner.person ID to be that particular value that you want it to be. Moving on, we will look at how these documents look like after they have been updated. So on the left hand side, you can see the structure where the primary owner in the primary owner struct, you have changed the value of the person ID by executing the previous update statement. Notice that the secondary owner's um, attribute is currently empty. It's denoted as an array of values, a list of values, but it doesn't have anything in it at the moment. We look into it very shortly. Now let's add a secondary owner to the vehicle registration. This is what I was mentioning earlier in the previous slide, is that the secondary owners list is currently empty. We are going to add a secondary owner to this particular exercise. So in this case, you can get the document ID in a similar manner of how we did earlier. You get the document ID for the particular person that you want to set as the secondary owner. So in this case, I'm again going to use the committed view of the person table, and I'm going to get back the document ID corresponding to the new secondary owner, which is Alexis Pena. So the condition is where p.data.firstname equal to Alexis and p.data.lastname is equal to Pena. Again, p being an alias for the committed view of person, and p.data denoting the structure or the struct that is contained in that committed view that corresponds to the business data that you are storing with you for your documents, and metadata is what you are obtaining from the metadata portion of that particular view. Step 2 would involve inserting this document ID corresponding to Alexis Pena's document ID into the secondary owners list. So we have applied an extension to PartiQL, which makes it very convenient to modify, remove, or insert elements within a document in QLDB. So for a given vehicle registration document, as found from the where clause, where it corresponds to a particular VIN value, we insert into the struct, secondary owner's attribute, a structure which has only one attribute called person ID. So insert into r.owners.secondary owners the value which is essentially a struct itself with the attribute name and the new value that you want. So let's now quickly look at how the document looks like after it's been updated. So on the left hand side, you can see that the secondary owner's attribute was an empty list. And now because we have inserted this particular structure containing the person ID and its value, you can now see that the secondary owner's attribute is list attribute is now has one value, which is a struct of containing one person ID. Now that we have modified all these documents, the vehicle registration document, QLDB allows you to query the revision history itself. So you can actually query the entire modification history of a particular document, say, for example, in the vehicle registration table. So similarly, what we had done before, we are going to be retrieving the document ID of that particular vehicle registration record in step one. So in step one, we select the ID from the vehicle registration table, alias as R, and we do not use the committed view. Here we are using the by clause, that is basically an extension that we have, a particle extension that we have supported in QLDB, which makes it very convenient for you to retrieve the document ID from the current view of the table. In this case, you are not going to the committed view, you're going straight to the user or the default view of for the table, which is simply referred to as vehicle registration. So select R underscore ID from vehicle registration as R an alias by R underscore ID. In the by clause, we refer to as the alias for that particular document ID as R underscore ID, where in the condition we have specified for a particular VIN number. And as we recall, this was actually an indexed field. Now, suppose the query returns the document ID of what's depicted here. We can now use this document ID to query the history function. So history in QLDB, like I mentioned earlier, is a particle extension that returns revisions from the system-defined view of your table. So it includes both your data and the associated metadata in the same schema as the committed view. So we're going to select h.data. So let's work backwards from the from clause. So from history, so history being a function, and the function taking one argument, which is the table name, from history vehicle registration as h, where h.metadata.id is equal to a particular value. So h.metadata gives you the struct or the ion structure that contains an attribute called ID, the document ID. And it also gives you the data portion, which is referred to as in the select clause as h.data. So win is essentially a data element in the document, an attribute in the document, which is retrieved as h.data.win. Similarly, it applies to city and owners as well. So h.data.win, h.data.city, h.data.owner. So essentially, now that we have retrieved these three distinct values, win, city, and owners, win and city being string literals, they appear simply as string literals. But the owners attribute we noticed was a struct, and hence it appears like a simple ion document itself, in which it again has two attributes, primary owner and secondary owner. But as you can see, you can now look at all the revisions that have occurred for the same VIN number or the same vehicle registration document, and it has gone through a number of changes, wherein the primary owner has changed, the secondary owners, which didn't exist before, we now have a secondary owner as well. So QLDB provides you an entire revision history of a particular document in your table. Now that we have looked at the fundamental concepts of how to model data, how to construct a particle query, and how to work with ion documents, it is time now to go and build an application with QLDB. We have provided you with purpose-built drivers, which are essentially client SDKs, in the popular languages, presently available for Java, Python, and Node.js, which are available on GitHub. And we would encourage you to go and use these drivers to build your application. For each of the drivers that are available in these three languages, We have also provided a corresponding sample tutorial, which is again based on the motor vehicle registration example that I just have gone through in the previous slides. Um, and you can use these sample tutorials to understand how you can use the driver SDK, the client SDK, to build applications. Thanks for attending the webinar and have a great day. We will now move to the Q&A portion of the webinar.